In science, we prefer to try and prove hypotheses to the best of our abilities, but because it's not yet proven, doesn't make it any less real. Consider black holes. Carl Schwarzschild envisioned the possibility of black holes within general relativity in 1916. John Michell, employing Newtonian physics, speculated they existed even before him, all the way back in 1783. But that means that for 55 years using relativity, or 188 years using Newtonian physics, we don't know about the theoretical possibility of black holes, but never actually saw any. The first black hole, Cygnus X1, was only spotted for certain in 1971. If it happened once, it's no stretch to believe it could be happening again. In the great ocean, scientific possibilities and wild imaginings, exotic stars and bizarre forms of matter may perhaps be those predicted, fecund, but as yet unperceived. What are these things? Who knows? That's the point. They're unproven. But I have some ideas. Stars are among the most stunning and inspiring objects in the cosmos. By violent thermonuclear processes, they release vast quantities of light, filling the night sky with light and warming up nearby planets in the process. By mergers and cataclysmic explosions, stars are also the cause of creating the dense elements, which constitute much of the matter we observe in the world around us. Astronomers and astrophysicists have made a long way towards comprehending how stars work, to the extent that we are able to forecast how long it will take before our sun exhausts its fuel and becomes a red giant. But today, we're not merely going to discuss the kinds of stars we know. Rather, we're going to consider stars we have yet to witness. Those that astrophysicists tell us could theoretically exist, including those that are essentially made of vacuum. First, we must establish some basics and get a grasp on how stars generally function, beginning with the most significant star of all, the Sun. Because the Sun consists of gas or plasma and not solid, you wouldn't be able to stand on its surface, as you can on the Earth. The gravity of the Sun would pull you in towards the center. So why isn't the gas on the surface being pulled inwards as well? It has turned out that a pressure is exerting outward from the core of the Sun to balance this gravitational pull. The source of this pressure mainly consists of the radiation generated due to fusion reactions in the core, the same radiation responsible for transporting light and heat from the Sun to the Earth. Whether you conceptualize radiation as individual, photons or waves in the electromagnetic field, its journey from the core to the outer layers of the Sun would cause an outward push in every direction. This radiation pressure would not be sufficient to prevent you from falling into the Sun, but it's sufficient to prevent the Sun's own gas, which is relatively light, from falling inward on itself. This tug-of-war between inward pulling gravity and outward pushing pressure is a characteristic of pretty much all known forms of stars. What the basis on which different stars are differentiated is where the pressure is derived from. For our Sun, the pressure is derived from the fusing of hydrogen into helium. When the Sun exhausts its hydrogen in around 5 billion years, it will be a red giant star, and will start producing its pressure by fusing helium into still heavier nuclei such as carbon and oxygen. The Sun will eventually exhaust its supply of helium and other light elements that would be able to be used as fuel for nuclear fusion. Then, it will shrink down to a compact star called a white dwarf. No further fusion is taking place any longer. White dwarfs are actually referred to as stellar remnants rather than stars. But if there's no longer fusion, where does the pressure to hold up these stellar remnants originate? It turns out that gravity compels the gas of a white dwarf inward until it's so dense that a new form of pressure arises, called electron degeneracy. Pressure. It's an entirely 537 purely quantum mechanical phenomenon, and it's the same phenomenon that keeps you from being able to 542 put your hand through solid things. Electrons just can't come that close to one another without an immense amount of energy. But certain stellar remains are so heavy that even electron degeneracy pressure isn't sufficient to overcome the force of gravity. This is referred to as the Chandrasekhar limit. It's entirely impossible to have a stable white dwarf any heavier than 1.4 times the mass of the Sun. If a star has exhausted all of its nuclear fuel and its center is heavier than the Chandrasekhar limit, that center will implode upon itself until it is so dense that an even more powerful form of quantum pressure takes hold, called neutron degeneracy pressure, which, as you might have suspected, keeps neutrons from becoming too close together. A star that achieves this state is referred to as a neutron star, the smallest and dense stellar class of objects known. Now you may be asking yourself, is there an upper mass that a neutron star could possess and yet be sustained by neutron degeneracy pressure? And there is. This time, it's roughly 2.2 times the mass of the Sun. Any heavier than that, and the neutron star would continue to collapse under the force of its own gravity, until, well, actually, not until anything. As far as we know, neutron degeneracy pressure is the strongest possible pressure that ordinary matter can exert. So there's nothing left to prevent a sufficiently heavy stellar remnant from collapsing in on itself forever. This is the fate that might await some of the most massive stars we've observed in the universe. From the perspective of an outside observer, these stars would become so dense that all we'd be able to look at is a black hole. That is a lot of pressure. Now, you may feel like you relate to that, but if you do, maybe it's time to start looking for yourself a new job. Something a bit more relaxed and enjoyable. You may want to try software developing. And yes, training, for that can be surprisingly fun. Thanks to the sponsor of today's video, bootdevboot.dev is no ordinary coding course. Their website feels more like you're playing a fantasy adventure, with quests and gamified elements that made each interactive task feel whimsical and entertaining. But at the end of it, you'll have written full projects, so it's a good way to get hands-on experience and skills. If you get stuck, there's a fantastic community who can assist, or you can chat with the AI bear. The initial chapters with all the interactive exercises are available to try for free. Then scientists began to ask themselves, what would happen to a star that wasn't composed of regular matter? If there were exotic types of matter which could hypothetically form even higher pressures than neutron degeneracy pressure, then what other types of stars might there be? You might suppose that we could simply repeat the pattern that we were beginning to observe earlier. Stars would be able to shrink even smaller and even more dense than neutron stars, provided that they were held up by some even higher pressure. You might assume that the only restriction on how tiny these stars might become would be at the point of no return, when they would become black holes. That point of no return is when a star shrinks below its own Schwarzschild radius. This is nearly correct, but not quite. Rather, physicist Hans Adolf Buchdahl demonstrated in 1959 that a star composed of any realistic type of matter, having positive energy density and pressure, cannot be smaller than 9 to 8 times its Schwarzschild radius. It doesn't seem like much of a difference, but that proportion of 9 to 8 implies that any realistic star must be appreciably bigger than a black hole, so it is much simpler to distinguish between them. And that's when physicists started wondering about stars that Buchdahl would term less realistic. For instance, suppose a star consisted of matter where pressure could be negative in one area and positive in another. In that case, Buchdahl's limit would not come into play, and that star may be smaller than 9 to 8 times its Schwarzschild radius. Actually, it may be infinitely close to the size of a black hole with the same mass. As an aside, theoretical stars, such as these which may be able to masquerade as black holes, came to be fairly a pain in the neck for astrophysicists, because now every time they found something they believed to be a black hole, they couldn't simply state that they found a black hole. They had to specify that it's either a black hole or an extremely dense object masquerading as a black hole, although in their minds they are pretty certain that it's a black hole. But back to the big picture. What would these strange stars with negative pressures even appear as? The answer is actually even stranger than you might have expected. Tolman, Oppenheimer, and Volkov came up with an equation in the 1930s that will tell you how the pressure of a stable star will change as you move outwards from its center. Today, it's simply referred to as the TOV equation for short. If the center of a star possesses a very attractive pull instead of a push, the TOV equation says that this star can only be stable and in balance with its own gravity if its pressure does something really wonky. First, the pressure has to blow up to -infinity somewhere in the star. Then it has to flip sign to +infinity and go downwards from there until it hits zero pressure, signifying the outer surface of the star. The precise position of the infinite pressure is determined by what the pressure is at the center, so if you adjust that central pressure to exactly right, you can keep the pressure finite right up until the edge of the star. That happens when the pressure at the center is exactly equal and opposite to the star's energy density there. In this special case, the TOV equations say that the pressure and energy density remain constant, equal, and opposite throughout the entire volume of the star, right up until its surface. If you've seen some of our other episodes, this might ring a bell or two. A constant positive energy density paired with a constant but negative pressure. That doesn't sound like any star we've seen before, but it's starting to sound more like a mysterious component of our universe: dark energy. And since the pressure and energy density in a gravastar are equal in magnitude, it's not just any kind of dark energy. Those are the exact properties of vacuum energy. That's why this special exotic star came to be known as a gravitational vacuum star, or gravastar for short. Inside of a gravastar, there is precisely zero gravitational force, because the positive energy and negative pressure respectively exert a gravitational pull and push that cancel each other out. And since the pressure in gravastars is constant, there is no pressure gradient to make any kind of push in one direction or the other either. So if you were inside a gravastar, you would neither be sucked in nor pushed out. You could float around freely, just as you would in an actual vacuum. Another curious feature of stars with negative pressures is that the closer you get to the special limit of a gravastar, which, if you recall, is when the infinite pressure surface gets pushed out to the edge of the star, the more their size approaches that of a black hole of the same mass. This leaves two important questions recently much in the spotlight among physicists. First, how can we determine if the very compact objects that astronomers have detected in merger activity and at the center of massive galaxies are black holes, or simply exotic stars with almost the same dimension? And second, if gravastars exist and are dispersed all over the entire universe, can they be the dark energy that's been accelerating the universe for the last 5 billion years? To solve the first question, physicists depend on the main distinction between black holes and other compact objects: the existence of an event horizon. You see, the defining feature of a black hole is that nothing that falls inside or even touches the surface of a black hole can ever come back out. On the other hand, if a star that is exotic is even a tiny bit larger than its Schwarzschild radius, it would not possess an event horizon, and it would quite possibly be capable of radiating information outward in the form of light. Not only that, but event horizonless objects would potentially possess unique signatures in their gravitational wave radiation compared to those of black holes during merger. This would allow us to tell them apart by measuring and analyzing those gravitational waves, using observatories like LIGO. But even with this battery of tests, it turns out that sufficiently small and dense stars can still be difficult to distinguish from black holes. So far, the best we can do is to say that the radius of the black hole candidates that we observe in the universe is at least roughly equal to their Schwarzschild radius. In some instances, that's just an approximation, but in others, we've worked that radius out to 40 decimal places. And as for that second question regarding dark energy, that's where it gets hot and heavy. In early 2023, an analysis led by physicists at the University of Hawaii found that astronomical observations of massive black holes showed them to be growing in mass over time, at exactly the same rate that dark energy would be expected to grow over time due to the expansion of the universe. They reached the inevitable conclusion that black holes are composed of dark energy, and that they are actually more gravastars than regular black holes with infinite density singularities in the middle. This conclusion was hotly disputed. Astronomers emerged saying that the interpretation of the observational data wasn't entirely correct, and theoretical physicists came out arguing that the expansion of the universe should have nothing to do with the growth of black holes in any case. So while the idea that dark energy could exist in the form of gravastars sounds exciting, it looks like the scientific community isn't going to be convinced unless it's simultaneously supported by better data and more compelling theoretical models. The opposite of a black hole. So while gravastars may exist, we're far from proving them, and they might look too much like black holes to be able to easily spot in the first place. But the next exotic object I'll investigate today ought to be as graphically different from a black hole as it's humanly possible. They are black holes' antithesis, the thrust to a black hole's suction. They are white holes, and there's no physical reason why they can't exist. I'd like to begin with a straightforward analogy. If I want you to visualize a cone, you'll likely think of something that points upwards, such as an upside traffic cone, or something that points downwards, such as an ice cream cone. These are what we consider cones in everyday life. But if you put down the most general mathematical description for a cone and attempt to graph it, you will end up with something that resembles two cones stuck together. You know, a mathematical cone consists of two halves, one pointing up and one pointing down, joined at their tips, and what we recognize as cones in the world around us are really only chopped up pieces of the full mathematical cone. Black holes are the exact same way. Let me explain. Many of the black holes we see out in the universe are the remnants of massive stars, whose extreme gravity caused them to collapse in on themselves. Once a black hole is created, it is forever isolated from the universe around it by a ball of stuff called the event horizon. Anything can enter the black hole, but nothing, not even light, can escape. This shape of space-time can be tidily encapsulated in what physicists refer to as a Penrose diagram, which is a method for mapping an infinite space-time onto a finite drawing. The essential feature of a Penrose diagram is that light moves upward at 45 lines, which makes it convenient to separate areas in which light can or cannot penetrate. Region 1 in this diagram represents the normal universe, with the initial star, prior to its having turned into a black hole, and everything beyond it, from the infinite past to the infinite future. Region 2 is the black hole, and it is divided from the remaining universe by its event horizon. You can observe how it's simple for light to fall into the black hole, Region 2, yet it's unreachable for light to escape. It will always strike the singularity instead. The same is true for normal matter, which travels more slowly than light, and so on this diagram can only travel upwards at angles greater than 45°. What's so interesting about this Penrose diagram is that it takes into account the creation of the black hole at some particular point in time, when the star collapsed in on itself. In the far past, there was no event horizon or black hole to speak of, and light could freely travel across all of space. But while this diagram represents the kind of black hole we're used to seeing in the real world, it's only one piece of the full mathematical description of black holes in general relativity. That is, it is the only ice cream cone of black hole diagrams. What if we then ignore the actual world and consider a perfect black hole with an infinite past, shorn of the baggage of dying stars and everything else in the physical universe? What is the analog in the black hole of the complete mathematical cone? It may appear to be an easy extension of our initial Penrose diagram, but this diagram has physics that is slightly inverted. Region 1 is still our ordinary universe, and Region 2 is still a black hole with an inevitable singularity in its future. But the mathematics also describes something that is a reversal of a black hole in Region 3. Rather than a singularity in its future, Region 3 contains a singularity in its past. And if you plot the path of light 4500 rays, it's easy to see that it's extremely for light to leave Region 3, but it can never enter it. This type of region is exactly what we would call a white hole. It's the space-time analog of a traffic's cone. But that's not all. If you move past the white hole, you will notice there is a region of space-time tagged Region 4, with the same relation to the black and white holes in the center as the normal universe. This region is a parallel universe, and it's completely separated from the universe in Region 1, because it's not possible for even light to travel between regions to regions. The result of all this is that the same mathematical formula describing the ordinary universe and the black hole also describes the parallel universe and the white hole. This doesn't mean that each black hole has a white hole attached to it, though. Similar to cones, the actual universe can have cut-up fragments of the complete mathematical solution. But this does mean that even if white holes are rarer than their black hole equivalents, or even if there aren't any white holes linked to our universe at all, it doesn't mean they're not scientific, in the sense that they're just as consistent with the laws of physics. In our analogy, if you can picture that ice cream cones are still very popular, whereas traffic cones are hard to make and phased out of existence, that doesn't make the concept of a traffic cone any less real. This is basically the state of white holes today. The idea of a white hole makes perfect sense, but it's possible that any white holes that ever existed in the past were unstable and were similarly phased out of existence. If you're wondering whether there might be some more stable white holes that have just gone out of sight, you're not the only one, and you should hang on for when we talk about the tiniest possible white holes in just a few minutes. But first, buckle up, because the Penrose diagram can describe more than just white holes. We're about to go to a whole new level of warped space-time, into the realm of wormholes and parallel universes. The no-hair theorem says that a black hole can have up to 3 intrinsic properties: mass, charge, and rotate. But the Penrose diagram I presented to you only explained the simplest type of black hole, which was electrically neutral and entirely not moving. The diagrams for a charged or rotating black hole are greatly more complex, but they're also greatly more thrilling, because they totally change our knowledge of singularities, and they give birth to new and interesting parts of space-time. Let's look at the Penrose diagram for a rotating black hole as an example. Rather than 4 different regions of space-time, there are now 8 kinds of regions that keep repeating themselves in an infinite series of universes. Regions 1 through 4 are the same ones that we saw before. These are the regular universe, the black hole, the white hole, and the parallel universe. But now that the black hole is spinning, its geometry no longer has an unavoidable singularity in its future, and the white hole similarly loses the singularity that was in its history. So, what really happens when you pass through the event horizon of a rotating black hole? Initially, you'll be pulled towards the center of the black hole, as you would anticipate. But finally, you will go past a point called the inner horizon, past which the geometry of space-time unwarps and allows you to prevent yourself from falling even further. At these innermost places, labeled 5 and 7, you are able to float freely towards or away from the center of the black hole. You might even reach out and touch the singularity if you wished, albeit I would not advise it. Here, in these most innermost parts of a curved, rotating space-time, you are technically in a wormhole, and if it weren't for the fact that you are forever cut off from everyone who remained in Region 1, this would have been the ideal time for you to brag about your wild space-time excursions. You're now also confronted with a sort of fork in the road. One choice is to continue moving inwards and circumnavigate the singularity, which would be ring-shaped rather than a point in the case of spinning black holes. This route would lead you to Region 6 or 8 in the diagram. But it's also highly likely that the presence of this route is an imperfection in general relativity's predictions and not a realistic outline of reality, since traversing even once around the singularity can result in causal paradoxes where you travel back into your own past. A better bet would be to turn around and head outwards, crossing back over into the inner horizon that you have just exited from. That would put you into Region 3, a white hole, which would proceed to shoot you all the way out to a whole new universe, the same structure as to one you began in originally, but unfortunately not with your family or friends waiting for you. Actually, by the time you arrive, your old universe will have already had an infinite amount of time. You would be existing in a completely new definition of the future. All right, let's get back to reality. As exciting as that trip through the wormhole sounded in theory, you likely couldn't make it in real life, and quite frankly, there's a good possibility that the wormhole itself would collapse when you disrupted its space-time. So how much of this mathematical structure can we hope to find in the real universe? Rotating black holes with event horizons seem to be omnipresent in the universe, but what happens inside of them remains relatively mysterious. There are two broad reasons why the physics within actual black holes could be other than what the Penrose diagram would have you think. First, when black holes result from the violent collapse of huge stars, a few assumptions that went into creating the Penrose diagram are broken, such as that the black hole existed forever, or that the universe around it is perfectly symmetric and doesn't contain random infalling humans. And second, the theory of general relativity used to construct the Penrose diagram might itself only be approximately correct, breaking down near the singularity where the curvature gets most extreme. So there's a good chance that some of the predictions of the diagram, particularly the most troublesome ones having to do with singularities and time travel paradoxes, are not actual characteristics of an extremely curved spacetime. But the possibility of white holes is more of an open-ended one, giving ample room for speculation about how they might exist and whether they may leave any observational traces for us to uncover. One theory that's recently gotten a little bit of traction is the idea that a white hole is created every time a black hole goes out of existence. And no, this isn't a fairy tale of reincarnation or voodoo, but a serious attempt to get at the complete life cycle of black holes, with at least some mathematical backing. Now, even a solitary black hole in an otherwise vacuous space will constantly emit particles referred to as Hawking radiation, making it steadily decrease and lose mass over time. But as soon as the black hole achieves the super tiny Planck mass, well, roughly 20 micrograms, we have no way of predicting what future awaits it, at least not without a full theory of quantum gravity. This is where loop quantum gravity comes in, a proposed link between gravity and quantum mechanics, in which space itself is made of discrete loops. In short, the equations of loop quantum gravity would predict that, rather than keep on shrinking to even smaller than Planck mass, such a minute black hole is more likely to quantum tunnel into a white hole and vomit out its contents back into the universe over a long span of time. Amazingly, although this white hole will be just as small and light, it will be able to hold a huge amount of entropy, because the geometry of its inside will have been pulled out into a thin tube with an incredibly large volume. This reservoir of entropy might be able to open up a channel for any information that is dropped into a black hole to be regained in the far future, resolving a long-standing issue in theoretical physics called the information paradox. When the white hole emits this information, it gradually disappears from the universe. The space-time around it flattens out, and its life cycle ends. In general relativity, our entire universe is going to have had a singularity in its past, that is 14 billion years ago, at time of the Big Bang. Thus, the universe is somewhat like an uncharged, stationary white hole. But if loop quantum gravity asserts that white holes are born when black holes evaporate, could the same be true of the formation of our universe? Could it be that our expanding universe was created from the remnants of an older, shrinking space-time? As wild as this sounds, loop quantum gravity asserts that may indeed be the case. So maybe white holes as a theory are not so outlandish. Perhaps it's time to begin believing in white holes. Because in a sense, perhaps we were in one. So white holes definitely could exist in the real world, even if we haven't absolutely nailed one down yet through observation. But I've skimmed over another sector of the Penrose diagram that would have raised an eyebrow. The Penrose diagram I employed had no problem referring to parallel universes, although that is a strong statement. Might whole universes, out of reach for ours, was our universe a coincidence, yet traveling parallel to us, just out of reach, actually be real? There's some logical reasons to believe so. But before we get to that, we need to turn our gaze to a baffling cosmic mystery, and the worst prediction in physics ever. It starts with a deceptively simple question: why is our universe expanding? One of the earliest things that you may be taught in a physics lesson is that gravity is an attractive force between two objects, the strength of which is proportional to the mass of each of them. Gravity holds planets bound in orbit around the Sun, and it even brings galaxies toward each other to create galaxy clusters and superclusters. But if we zoom in a bit further, this gravitational pull starts working the opposite way, and galaxy clusters begin moving away from one another instead of attracting each other towards them. So what's going on here? Einstein's theory of general relativity provides us with an understanding of this bizarre behavior through the lens of space not being just some background upon which other things move around, but rather the space itself can be stretched and bent and change over time. Einstein demonstrated that within this context, gravity is not a force, but a warping of an object's inertial path in a dynamic space-time. For instance, when a planet orbits the Sun, in Einstein's explanation, it's simply taking a straight-line path in a curved space. This means what we see as a repulsive force between galaxy clusters really ought to be considered an accelerated stretching of the space between them. But what could be responsible for the acceleration of the expansion of space on the grandest scales of the universe? To start answering this question, we must understand what makes space-time warp and stretch in the first place. In Newton's theory of gravity, everything with mass pulled on everything else gravitationally. And in general relativity, everything with mass warps the space-time around them. But Einstein demonstrated that in addition to mass, any energy or pressure form will also affect the space-time's dynamics. Energy density is the amount of energy contained in a specific volume, the amount of pop, heat zap, and motion contained in a specific space, and in our universe has consistently been discovered to be positive. Pressure is the amount of force over an area the contents of the space exert, pushing into the rest of the universe surrounding it. Think interstellar dust pushing against each other whenever they collide with one another in the void. As you can imagine with objects so far apart, this pressure value floats a tad over zero on the cosmic level. When these values are accumulated positively, such as in the following equation, their effect upon the space surrounding them makes the space around them shrink in. In effect, they generate gravity by slowing down the extension of space. However, conceivably, if you were somehow to set the values of this equation so that pressure was negative and greater than the positive energy density, that minus sign would cause the whole thing to flip, and you would accelerate the stretching of space. In effect, you would end up with a volume of space filled with a kind of anti-gravity, a dark energy. It's a little nebulous, as it's tricky to visualize anything with a truly negative pressure. How can you have less than zero atoms in a patch of space after all? But atoms are not the only things that exerts pressure. After all, pressure is simply a force applied across an area. Fields can also apply forces. Think a magnetic field, dragging a piece of iron in towards a bar magnet, or two magnets pushing each other away. If dark energy were some kind of field that pushed away not only other magnets, but anything, then this would be consistent with what we observe the universe to do, vacuum itself containing dark energy, and plenty of it to very gradually, very slowly push the universe apart. Scientists have given much consideration to dark energy through the years and even determined what its collective energy density and pressure must have been to produce the rate of space expansion we see. It's in the order of 10 to 9 in SI units, which is a very tiny number, which is why we can't feel it here on Earth and only see it on the grand scale of the universe. This is in fact good news, since it turns out that if the number were much greater or smaller than this, things would get very bad for our possibility of being. Let me illustrate what I mean with a brief sketch of the history of the universe. Here is the whole history of the cosmos, from the instant just after the Big Bang to today. This is dark energy density as measured by astronomers. Scientists think its negative pressure has maintained this density roughly steady for billions of years, and even though there's fresh evidence emerging that indicates dark energy is slowing down over time, for our arguments we can simply maintain the value unchanged. It doesn't alter the argument we're presenting, as you'll soon see. This is the density of common matter within the universe, which contains negligible to no pressure. The density goes down with time since the expansion of space dilutes the matter within it. Finally, this is the density of radiation in the universe, including photons and other extremely light particles. The positive pressure of radiation makes it dilute away even more quickly than ordinary matter. Towards the beginning of time, for a very short period, there were no atoms. Very quickly, though, protons and neutrons melded together to form the very first atomic nuclei in the early universe. Later, after matter had become the leading form of energy, the universe had cooled sufficiently for nuclei to capture and retain electrons and form the initial atoms of hydrogen and helium. These atoms formed the raw material of the very first stars, and these stars were gravitationally pulled together to create the very first clusters and galaxies. Dark energy only later took over, triggering the accelerated expansion of space and preventing larger structures from forming. But what if the energy density had been greater? Imagine what would have occurred if the dark energy's pushing power had been greater. It might have been sufficient to stop the process of those early galaxies from forming, pushing stars more strongly than their own gravity could attract them together. A little bigger than that, and it would have been really hard for any stars to be formed either. And if dark energy density were big enough, we practically wouldn't have had any atoms or even nuclei to be formed in the universe. So that's what it might have been. What should it have been? By doing some clever math and the rules of quantum field theory, scientists tried to extrapolate how much the energy density of dark energy should have been. What they got was greater than the value we observe in nature. How much greater? Their number came in at an unbelievable 1045 joules mm3. Where does the predicted energy density of 1045 joules per cubic meter plot on this graph? It's literally off the charts. If that prediction were true, the universe today would have no form, no features, no life. It would be a giant vacuum full of nothing but dark energy. And if the dark energy density were instead a negative 1045 joules per cubic meter, the destiny of the universe would be no more auspicious, as it would be compelled to contract in on itself very quickly in what's called a big crunch. So that is the mystery. Why is dark energy density so much less than we would expect, at the very level that it had to be in order for life? Scientists have tried to explain their figure being so far off by proposing that there are particles with positive energy and negative pressure, as yet which flattens the maths and returns the dark energy density answer back down to zero. Maybe there is a huge negative potential energy source which levels all the maths out, some kind of cosmic stretched spring which somehow holds all that wild energy in check. Either that, or quantum field theory is outright incorrect. But as there's really quite a bit of evidence in favor of quantum field theory, it would appear imprudent to discard the notion entirely. Rather, we are left wondering at the wondrous nature of this cosmic coincidence. What were the chances that the density of dark energy would be so low when it was supposed to be so much greater? That this grand balancing act of the universe happened so that we weren't ripped apart or smushed into a singularity. Without it being so low in scale, we wouldn't be here. Our very atoms would never have come together, torn apart by surging, expanding space. According to our predictions, we have got very lucky. This coincidence happened in such a way that the universe was able to produce life. So, was it a coincidence? How many universes are there? Of course, there are different explanations for this dark energy density problem, usually referred to as the cosmological constant problem. Those with a religious bent would cite the concept of intelligent design, that this wasn't so much chance as purpose. A god, or very advanced entity, has determined the density of dark energy to be just so that life can exist for the purpose of creating us. Of course, this idea doesn't sit well with everyone. The existence of a godlike being by nature is difficult to prove or disprove, and taking such matters on faith is not really what science is about. For many scientists, a different sort of answer was needed, and that solution came in the form of multiverses. Let's travel back to 1987, when the exact value of the dark energy density in our universe had not been measured yet. But obviously, that was very tiny or zero because, well, we were there, and so was everything else in sight. In that year, physicist Steven Weinberg wrote a paper linking the universe's luckily low dark energy density with something called the anthropic principle. Basically, the only universes in which we are able to assess the probabilities of are the universes which had the appropriate conditions to evolve into us. If the universe hadn't rolled so an improbable roll of the dice, there wouldn't be us to observe whether such things were more or less likely. If it requires an extremely improbable roll of the dice to create people, then a universe where that roll of the dice actually occurred is the only universe we might ever observe. Weinberg could be more precise than that. He was sure that the horizon of dark energy density for creating life would be no lower than the threshold for forming galaxies. In other words, by the time galaxies have formed, you've probably crossed the threshold to where life can form too. After all, how else? Was life supposed to arise if there were no stars and galaxies to provide complex building blocks and energy? During his time of publication, observations of a very old and far-off quasar had shown that galaxies had already started forming just 1 billion years after the Big Bang. Weinberg utilized this data to estimate that the development of these old galaxies demanded the dark energy density to be less than approximately 10 to 7 JM3, which implied that, taking it was assumed that galaxies were indeed needed for life to emerge, the minimum dark energy density for life to occur was smaller than or equal to this value, though not so small as to be negative. Weinberg originally argued that if the dark energy density were considerably less than this figure, then some other factor besides anthropic reasoning would have to account for the smallness of the dark energy density. But as it happens, the actual dark energy density is nearer 10 to 9 JM3, which isn't very different from the 10 to 7 cutoff found by Weinberg. That is to say, life and dark energy density go together unexpectedly well. Of course, this pays no attention to one important point. Just because we can observe universes where we do exist does not mean that it is necessarily so that we should exist. We might simply not have existed at all. I mean, the probability of the cosmological unlikely. Could the diverse contributions to the dark energy density have canceled out to a value consistent with life by pure chance? Not likely. Here's what would have had to have occurred. Imagine making 3 random real numbers in the interval, 1 to 1, summing them up, and hoping that the absolute value of the sum is at most, with 55 zeros. It sounds just about impossible. But what if we had more than one go at it? What if we could generate those numbers over and over and over again until we got lucky? It might take us something like 1056 tries, but given enough time, the unlikely cancellation of 3 randomly generated numbers will turn into an inevitability. We can apply the same reasoning to possibly explain why the high density of dark energy is so strangely small. Rather than one universe, consider that there does exist a huge multiverse, with every universe containing a different, arbitrary value. For the dark energy density, only a small fraction of them would have a dark energy density small enough to be compatible with life, but that's precisely where we humans would expect to find ourselves. This explanation has no coincidences, no fine-tuning, no intelligent design, only a whole lot of different universes. By itself, the concept of a multiverse would remain too general to be decent science theory. To begin with, what type of multiverse are we discussing? How do they exist at all? Luckily, there are actually several competing notions of multiverse that physicists can use to describe things. First, there's a multiverse divided by time. If you know about the Big Bang and the Big Crunch, you will understand that it's usually thought that this creation and destruction of the universe is an endlessly recurring process, with new universes appearing each time. If the underlying figures of each universe are a little different with every iteration, say if dark energy density can vary from universe to universe, then after a sufficient number of Big Bangs and Big Crunches, you could necessarily have a universe with a dark energy density precisely like our own. There are a few assumptions in here of course, since we don't yet know for certain that the universe does curl up into a big crunch. But if it does, and if the laws of the universe are slightly different with each new cycle, then this is a working model for a multiverse. A second multiverse explained by physicists, although one that I personally find a little bit more questionable, is a multiverse divided by space. Even though the laws of physics appear to be constant across all of space that we can observe, there are regions of space that are unobservable, parts of the universe that are moving away from us in a speed from us so fast we never will experience light from them. It's theoretically possible the rules of these regions of the universe might be different from ours. And if this happens, then we are basically in a different kind of multiverse. I find this model less satisfying, although both for the reason that it sounds odd to label a more distant region of our universe a different universe merely because we cannot observe it, and also because there is no indication that the laws of physics vary with place. This strikes me as the most unlikely kind of multiverse. But finally, modern physics describes a third type of multiverse, one that is disconnected from our space-time entirely. In the many worlds interpretation of quantum mechanics, every macroscopic interaction or measurement of a quantum state causes the wave function of the universe to branch into multiple non-interacting parts. If you've heard of Schrödinger's cat, you can picture the universe branching into one universe in which the cat is alive and another universe in which the cat is dead. With each such encounter, the number of universes increases exponentially, and the quantum multiverse becomes increasingly richer and more diverse in its description. To clarify, we still don't know whether this branching process is the right physical description of quantum mechanics, but it is probably the simplest, and it is exactly consistent with all the experimental data. Or at least, we have no evidence that it isn't that way. If it does turn out to be correct, then it would add a whole new layer of complexity to our understanding of the multiverse. Multiverses are useful in that they remove the need for massive coincidences or intelligent design as a way of explaining our presence in the universe. However, are they actually real? Unfortunately, the answer is an unsatisfying, we don't know. Although the differing multiverses do assist in resolving the cosmological constant problem, we really have no proof that they actually exist beyond the provision of an explanation for that coincidence. We have no evidence that the laws of physics are different space or time or quantum universes. If other universes exist, they might have exactly the same laws of physics and values for dark energy density as our own, which would put us right back to the same problem we started with. How are we here when the odds of the galaxy itself existing is 1056 to 1? Or worse, the dark energy density value is 1056 to 10120, smaller than predicted by our theory. And the way we will get that proof will be tough. We are going to have to survive a big crunch, or travel into a region of the universe that's too far away for even light to move fast enough to return from, or travel into another quantum universe somehow. All appear impossible, or at least highly improbable, and maybe the type of journey you can't come back from. That may be just as unprovable as God's existence. So you are free, in a sense, to believe whichever one you find most comforting. Or perhaps just hold on until a better way of answering the question can be discovered. And really, whether it's parallel universes, wormholes, white holes, or gravastars, the theoretical terrain of science is full with potential. And let's not forget, there is more than enough sound precedent for what-ifs becoming reality. Black holes, the planet Neptune, the existence of antimatter, or the cosmic background radiation itself, all were discovered in theories prior to being found in practice. We are living in an era where our mind's eye is often surpassing our visual eyesight, where maths and equations are leaving any detection equipment or telescope in the dust. To me, it's amazing that we reside in a universe based on rational rules that make such conclusions possible, where we can Sherlock Holmes reality. The laws are so predictable that once we grasp them basically, the rest of the universe just naturally emerges. I love the organization of it, and the miracles that are possible because of it. So, could these things actually be real? Yes, if we have gotten the theory right. And if we haven't, then I don't know what bizarre and jaw-dropping occurrences science will next forecast as things get clearer. And naturally, the day when what we envision is no longer purely a figment of the imagination, when we finally catch sight of those actual counterparts awaiting us in between the stars.